welcome to New College. We are so happy that you're here and you found us amidst the traffic on this absolutely gorgeous day. Before we start, I really want to thank our sponsors because they help make this happen every time we have it. And tonight we're thanking WEDU, PBS in Tampa, and the Herald Tribune, as well as the Courtyard Marriott and Treviso just at the Ringling. So I'm really happy that our speaker came to talk to us today, in part because he's a New College alum. And so we're always really excited when a New College alum comes back. And he has done amazing things, and we get to take credit for some of that because his intellectual journey began in part here, so we're happy about that. And I just want to tell you a few reasons why we are celebrating having Jeff here tonight. One is that he is a really good scientist, and he's had more than 60 grants, more than 200 publications. But the cool part about it is how many areas he's hit, from wetlands to carbon sequestration to pineland to pines. So all kinds of different areas and all the different people that he's worked with, so many different disciplines, really from like dolphin scientists to climate folks to anatomy, all kinds of different people. You can't imagine. It's such a cool list of folks that he's worked with. One of the things that he might be surprised I say about him, though, I should just say now he's a named chair at FSU, and so he's done very well, and he speaks to all kinds of people. I probably made him sound a little too sciencey. He's a real authority, but he can really give a talk. So, phew, for you. And he's talked all kinds. He talks to community groups all the time, so he gives back, and he thinks about that a good deal. And he's actually instructed our governor on climate change, so that's a heartening thing. But one of the things, listen, he gives the information. That's his job. One of the things, though, I really liked about him when I talked to other people who were at New College when he was here was that I think he really got the college. So every one of our students has to do our senior thesis. And so Jeff, when he got to his senior year in chemistry, he had to do a senior thesis, which is, data collection, lots of time in the lab, analysis, writing, rewriting. Then you have to defend it to 3 faculty members. And during that year, he realized that he was really going to be a scientist, and he was going to be sort of, a little bit stuck in science, but that he was at a liberal arts and sciences school, and he should take advantage of it. So his senior year, he took sculpture, poetry, and literature. And they were really challenging. I mean, he was good at chemistry, but this stuff was sort of out of field. And so I think that means that he must have really gotten the place for 2 reasons. One, the point of a liberal arts and sciences education is it makes your life better. It's about quality of life. So I'm guessing you probably had some poetry, sculpture things to work on, but that's good. But it means that you could embrace risk because we have that kind of flexibility. And it's much better that he wound in the world knowing about poetry and sculpture. Another great thing about Jeff is that his oldest child came back to New College and graduated from New College. So I think that always makes me feel good about the college. Just keep sending, more grandchildren. We're hoping for them. And he's a really interesting person, and I have evidence of this is because he got this really cool woman to marry him, Susan Cerulean, and she's a nature writer. She helps us sort of embrace the beauty of Florida and think about our resources. And she has a third book coming out, and I don't want to get the title of that wrong, so I'm going to actually look that up. And that is Coming to Pass, Florida's Islands in a Gulf of Change. So that's about to come out. And finally, I'm just thrilled that Jeff's here because he's going to talk about one of the biggest challenges we're facing right now globally, and that is major environmental change. So I could keep listing all of his attributes, but I can't because he's literally going to try to cover 1 million years worth of data in his talk. And so I'm looking forward to seeing how that happens in 45 minutes. But I think he's going to do it, so I'm looking forward to it. Please welcome Dr. Jeff Chanton.
Okay, thank you all for having me. And I thank y'all for supporting New College because it was a really good thing for me, and I really appreciate it. So this is the Maldives, which is an island nation in the Indian Ocean, and as the Maldives are to the world, Florida is to the United States. This is a really crowded little island, as you can see. It's only less than a meter above sea level. There's a wall around the whole thing. And this is the country that is always protesting at United Nations about climate change. Like, what are we going to do about climate change? Because all those folks, there's over 100,000 people that live on that tiny island, and they have nowhere else to go. It's not like they're going to be able to move to Australia or come across into Nevada or Arizona. So they're very concerned about it. And so you can see that we have the same problem here. This is a picture that's really striking. This is New Jersey after Hurricane Sandy, and that roller coaster was not built in the ocean. The ocean came to it. Okay, so sea level rise is really the thing about climate change that we need to be concerned about here in Florida. If it gets a little hotter, well, we don't care about that. You know, we like it hot, but sea level rise is the issue, and I'll explain what that's all about. So this is the famous Keeling Curve, and Ralph Keeling was a graduate student in the 50s, and he measured the CO2 concentration in the atmosphere, in the troposphere. And you can see, of course, everyone's familiar with this curve, I think. And if you all have any questions while I'm speaking, please just raise your hand and don't let me go past something that you don't get, okay? So this is parts per million of CO2, ppm, microliters per liter in the atmosphere. And this is the year going back from 1958 to, this stops in 2004, but the record doesn't really stop. And so you can see that there's two trends to this data. One is that there's an increase from 315 parts per million, and now it's at 400 parts per million in the atmosphere today. And you can also see this seasonal change, this sawtooth pattern, which is the greening of the northern hemisphere in spring. So the northern hemisphere is where all the land is. Southern hemisphere doesn't really affect that very much. So this is the terrestrial biosphere, the plants, the deciduous trees, and in the springtime they take up CO2 when they leaf out, and in the fall they give that CO2 back because the leaves fall on the ground and they are respired. So that's microbial. So the first thing you see is that the biosphere can affect the atmosphere, and that changes on the order of 5 parts per million every year. And so if the biosphere can affect the atmosphere annually, then we might expect that our activities as human beings can affect the CO2 concentration, as we've seen it go up from 315 in 1958 to over 400 today. Okay? The thing about the CO2 is a waste product, okay? It's a waste product from fossil fuel combustion. And it's a waste product that comes out of the smokestacks from our power plants, whether it's coal or natural gas. It's a waste product that comes out of our tailpipes when we drive around. And every other waste product you pay to dispose of. You take care of it. So when you flush your commode, you pay for sewage. And we treat that sewage before we discharge it to the environment. When you take out your garbage, you pay to have that removed. And it's put in a landfill and taken care of. CO2 is the only waste product that's freely dispersed into the atmosphere, into the environment, with no charge. You can dump it for free. And that's what we call, we all subsidize that, okay? That's an externality. So you dump that into the environment for free, but people pay for that in other ways. It's an externality. And the atmosphere is the absolute worst place that you can put this waste product, because you know the ocean has a lot of mass and density, and the land has a lot of mass and density, but the atmosphere is very thin, and the total mass of the atmosphere is very low. So we have the hydrosphere, that's the ocean, the lithosphere is the solid earth, and the atmosphere is the air, and the atmosphere is very thin, and so you can easily affect its composition with waste products, and yet that's dumped out for free. Okay? So the way that we do that is we take ice cores, and this is a very simple approach. This might be how they do it in Greenland. We also do it in Russia. The Russians help us do it in Antarctica. So we've taken ice cores in all the places where snow is accumulating. And the snowpack accumulates over time. And so in this instance, depth is time. And we get an ice core, and here's a picture of an ice core. So as you go deeper in the ice pack, you're going back in time. So you have what we call a chronology. Chrono means time. A time sequence. Okay, so going down this ice core, we can get a history of the atmospheric composition. And we do this. This is a pit that's been dug in the ice. And this guy's standing next to it. You can see those little annual layers. That's, these things form during the warm periods in the Arctic or the Antarctic. And a little bit of melt. And so these are like tree rings. And so you can get the time sequence. You can get the time sequence from these annual bands, like a tree ring. Okay? So that's time. And as this accumulates upward, the snow turns to ice sheet. And I keep hitting the wrong button. As the snowpack turns to ice pack, it traps little samples of the atmosphere within it. If you remember from reading Jack London, when the huskies are cold at night, they burrow down into the snow. So the snow contains a lot of air. Okay? So here's the snow. And then that snow coalesces and turns into ice sheet. And as it does that, it traps those air bubbles within it. And then it's building up higher and higher. It's accumulating over time. And so on the Earth, these ice sheets, as they've built up over time, they've taken samples of the atmosphere for us, okay? It's like we had some graduate student out there putting samples of the air in little vials going back a really long time, okay? 1 million years. So this is taking samples of the atmosphere for us. So we can go in the lab and take this core, slice it up, and put it into vacuum chambers and melt it, and then the ancient atmosphere is given to us, and we can analyze its composition and see what's happened. So the records that we've gotten, and I'm just going to call your attention to the CO2 record because we don't have time to talk about them all, but here's the CO2 record, and here we have time on this x-axis going back to the year 1000, and there's the year 2000, which will be like today, okay, even though it's not 2000 anymore. And what you see is the CO2 concentration was flat at about 280 parts per million. Now that Keeling graph started at 350, okay? So back in the pre-industrial times, it was 280. And it was very linear and not doing anything. And then around 1800, you can see that it began to increase, okay? And you know what that was, right? What happened in 1800? The Industrial Revolution. And they started to mine coal in England. And when they started to mine coal in England, the CO2 concentration, as we burned that coal, I keep hitting the wrong button. Sorry. These buttons are killing me. All right, so the concentration is linear at 280 parts per million. We start to mine coal, and it goes up to 400. This is another greenhouse gas, methane. This is what comprises natural gas, and you can see that it's had a 240% increase over the same period of time. Okay. Yeah. Uh-huh. Well, the atmosphere is well mixed, okay? So the atmosphere mixes on a time scale of like about, well, you can see those seasonal variations. So it's faster than a year. So anything you emit into the atmosphere in England, it's all over the whole globe in a time span of a heartbeat, basically. Okay? Yeah. Oh, well. Yes, it would. I am not paying him. So, yeah, interestingly enough, the human population mirrors the greenhouse gas concentrations. And I just said these are waste products, right? And so this is our waste that's building up in the atmosphere around us. It's a waste product from our industrial respiration, okay? Like respiration, we eat ham sandwiches, we breathe out CO2. Industrial respiration takes in fossil fuel and breathes out carbon dioxide. And that has allowed our population to blossom, okay? And I'm an oceanographer, so I know sometimes it happens in the deep sea that they have these things called whale falls. And a whale carcass will fall into the deep sea. Now, normally the deep sea is a pretty barren place. There's not a lot of life on the seafloor in the very deep sea. But when that whale carcass falls, then life explodes and you have a big population increase when that resource is supplied. For human beings, the whale carcass is under our feet. It's fossil fuel, okay? And so that's allowed our population to grow. This is the same response that you get when you put bacteria in a jar with chicken soup, right? So human beings are acting like biomass. Okay, we're just doing a typical biomass response. And it's time to get a little more conscious about what we're doing, or we're going to suffer the same fate that the bacteria suffer in the chicken soup broth. Okay, so we need to be conscious about what we're doing. And that's the message. Okay, so this fossil energy source allowed our population to bloom. Okay, the way this works is CO2 and methane they make the atmosphere more translucent. Okay, so the atmosphere of the Earth, shown here, is transparent to visible radiation. Most of the rays of the sun are of the visible wave band. So the rays of the sun pass through the Earth's atmosphere. And the Earth's atmosphere is transparent to those sun rays. And then those sun rays, when they hit the surface of the Earth, half of them are just reflected light, still visible radiation. Just like moonlight is reflected light, okay? So half of the sun's rays come in and they're just bounce off, they're reflected. And that's called albedo, that's the Earth's reflectance. The other half are absorbed and they're redshifted and they're re-radiated back as infrared radiation, a long wave radiation. So the visible light, half of it comes in and it hits the Earth and it's re-radiated as heat or infrared radiation. And the greenhouse gases, CO2, methane, and also water vapor, they act as a blanket and they trap that infrared and they warm the surface of the Earth. And the greenhouse effect is a good thing, okay? Because without it, the Earth would be a frozen ball. All the water would be frozen. So we want a greenhouse effect, okay? That's good. Well, I'll come back to this, okay? So the greenhouse effect, in essence, is good. What's tricky for us as humans and having a large population is change, okay? So we have to be aware of what could change and manage that. Okay, so any questions about this? It's just like a car. You park your car in a mall parking lot. You go in, you roll up all the windows, and the visible radiation goes through the glass of your windshield. And it's absorbed by the seats of your car, and it's re-radiated as infrared or heat. And the windshield is transparent to the visible radiation, but it's translucent to the infrared radiation. So the rays come in, the energy comes into the car, it's absorbed, it's phase shifted, it's red shifted, and it can't get out. And that's the way the greenhouse effect works. Okay? Any questions? Okay. So let's talk about a longer climatic record. Okay? We're going to go back even further in time. We've gone back 1,000 years, and we saw that the pre-industrial CO2 concentration was flat at 280. And then it went up to 400 in an exponential way, meaning faster and faster and faster, okay? So going back further in time, and this is based on ice cores from Antarctica, okay? The earlier ones I showed you were from Greenland. There the ice accumulates faster. In Antarctica, it accumulates more slowly, so you can get a longer time sequence over a shorter depth. So it turns out that over the period that we call the Pleistocene, the ice ages, you've heard that term, right? Pleistocene. Over the Pleistocene, the Earth has had two climatic channels. You remember in the old days when the TV had channels and you could flip from channel A to channel B? Well, the Earth's climate has two channels. It's digital. We have a digital climate. And it goes from glacial state as shown here, when the ice is accumulated on the continent and it goes all the way down to New Jersey, and then it goes to interglacial state, which is kind of what we're in today. We're in an interglacial state today. So during a glacial state, you have ice, a lot of ice on the surface of the terrestrial surface. You have a lot of water removed from the ocean, stored on land as glaciers. And during the interglacial, you have less ice, you have a frozen Antarctic, and you have Greenland ice sheet. Okay, but for the most part, the ice cap has receded. And so sea level varies with this too. Okay, when you have this kind of state here, the glacial state, you have a low sea level, and this state you have a higher sea level. And sea level changes by 300 feet, going from a glacial to an interglacial. Okay, so sea level changes by 300 feet. Okay, in the interglacial, it's high, and during the glacial period, it's low because you take water out of the ocean and you store it on land as ice. Okay, and these changes in the Pleistocene were driven by what kicked them off, what started them, what pushed the rock rolling down the hill is changes in the Earth's orbit, okay? And the Earth's orbit is influenced by the other planets, and it goes through these shifts from very round to more egg-shaped, okay? And so when it's like this, you have an interglacial, and when it's like this, you have a glacial period. And there's very slight changes in the amount of sunlight that comes into the Earth. And what these do is they drive these cycles of glacial to interglacial state. So what happens is a little bit of, well, let's look at the data here first, okay? So this is a record from an ice core in Antarctica. And what you see here, this is now, here's time 0, and we're going back 800,000 years. So that's almost a million years, 800,000 years. And this black record here is temperature, and the green record is methane, the other greenhouse gas, and the red record is carbon dioxide. And so let's just look at temperature here first, okay? And you see here is this is the present interglacial. This is time 0. It's warm now. The ice sheets have receded. And you can see that we've been in this interglacial for about 10,000 years. And then before that, we were in a glacial period. Then here's another interglacial, about 100,000 years before. Then here's a glacial period. Here's another interglacial. Here's a glacial. Here's another interglacial. There's a glacial. There's another interglacial. It's a very clear pattern for 1, 2, 3, 4, 5 interglacials, and then it gets a little noisier, okay? So that's the temperature. Yes?
Can you establish cause and effect there? It almost looks like the elliptical ground curve at the bottom.
Mm-hmm.
The temperature shifted before the gas percentage.
Yeah, right.
So what caused what?
I'm going to come to that, okay? But the next thing is, you notice that these gas concentrations are correlated with the temperature, right? So when the temperature is high, the methane is high and the CO2 is high. Temperature is high, methane is high, CO2 is high. Temperature is high, methane is high. And when the temperature is low, the gas concentrations are lower. Okay, so remember that concentration that we saw in the pre-industrial was 280, right? This CO2 concentration up here is right at about 280. So for some reason, during all these warm periods, these interglacials, the CO2 concentration kind of gets to 280 and flattens out. And then at the bottom, during the glacial periods, it gets to 180 and flattens out. Okay? And then the methane's doing about the same thing. It's following the same pattern. So at the very least, we can say that temperature and CO2 concentration have a really good correlation. Okay? I'm going to come to causality in a second. They have a really good correlation. And when it's, and the temperature variation you see is about 8 degrees centigrade. Okay? And the CO2 concentration variation is about 100 parts per million, from 280 in interglacials and like pre-industrial to 180 during the glacial periods. Okay? So we're changing CO2 by 180 or by 100 parts per million, and we have an 8 degrees C temperature variation correlated with that. Okay? Now, what leads this off is the changes in the Earth's orbit and slight variations in sunlight, which are, they kick it off. Okay? So, right, the temperature leads because the orbital variation starts the temperature to increase. And that temperature increase causes the CO2 to degas from the ocean because gases have what you call retrograde solubility. They're more soluble in cold water than hot water. So the sun gets a little brighter, it warms the ocean, the CO2 degases, and when that CO2 degases, it causes the planet to warm up a little more. And then it warms up a little more, so it degases some more CO2. And so you have what's called a positive feedback. Okay? And so it's like, if I can push the right button here, it's like a rock rolling down a hill. Okay? What kicks that, the rock is sitting there. What kicks that rock into motion is changes in the Earth's orbit and a slight increase in sunlight. But that change in the Earth's orbit and that slight increase in sunlight are not enough to drive 8 degrees C temperature change. You need this positive feedback of the warming, the CO2 evolution, followed by more warming, followed by more CO2 evolution. And it cycles like that. Yes?
Does the modification of the magnetic north or the axis under which the Earth turns play a role?
Yes, there's three, and that gets more important. There's three variations in the Earth's orbit. One is this eccentricity, the other is the wobble, and that gets more important back in here. You know, and that has a 40,000 year periodicity. There's another thing called the precession of the equinoxes that I won't try to explain, but you can Google it. And that has about a 20,000 year periodicity. So in the last 5 cycles, the eccentricity was the dominant term. Before that, the wobble of the Earth's axis was the dominant term on a 40,000 year.
Plus the total term of the magnetic field. Because the north and the south.
Yeah. That, I don't know that that affects climate, though. That's a good indicator for seafloor spreading. Okay, so going back to this, you know, I think I've explained it, right? It's changes in sunlight associated with Earth's orbit lead to positive feedback by evolution of CO2, which causes more warming and more evolution of CO2. Okay, and so here we are. This is just the CO2 concentration isolated for the last cycles. Present interglacial, we saw that the pre-industrial CO2 concentration was 280. There's 280 marked here in this dotted line. And this interglacial, 100,000 years ago, it always gets to about 280. The lower limit's 180. Okay? So, and right now, we're at 400. Okay? So the CO2 concentration is out of bounds of anywhere it's ever been for the last, well, 800,000 years. That's pretty clearly obvious. And the trend is, if at the rate we're consuming fossil fuels, by the year 2100, it will be 700 parts per million. Okay? And we've seen that there's a clear correlation between temperature and CO2 concentration. Okay? When CO2 varies by 100 parts per million, the temperature varies by 8 degrees C. We've added another 120 parts per million of CO2 already, and we're going to add another 300 by 2100. So, I mean, it might give you pause. You might think that the temperature could respond to this, okay? I'm not saying it will, okay? But there is a strong correlation going back for 800,000 years that they vary together. So you might be concerned, if you were a leader, that there'd be some kind of temperature change associated with this, and you might want to act in a preventive measure. We all get house insurance, right? We all pay homeowners insurance because we might have a fire in our house, right? So why wouldn't we take care of our one planet? You can always get another house, but we have not got the capability to go into the stars yet. Okay. And not only that, you know, like by 2100, it's going to be 700 parts per million. But there's enough fossil fuel reserves on the Earth. You know, all the fossil fuel that Exxon and Peabody Coal and all these energy companies have that determines the value of their stock. Their stock is based on their holdings. Their oil in the ground, their coal in the ground. That's what makes Exxon worth so much money, right? But I think if we burned all their reserves, if they were able to cash all that in, we would not have a world like we have now. It would be a different world. And I'm not saying that the Earth can't go through that. The Earth will be fine. It's a human comfort and civilization thing that would be at risk. Okay, in the Cretaceous, and that's, you know, going back 6,500 million years ago, there was higher CO2. It was 1,500 parts per million. And the Earth was warmer. There were no ice caps at all. There was not an ice cube to be had on the whole planet, okay? Because there was no freezers, you know? You could not get ice for your Coke. It would have been impossible, okay? There's enough fossil fuel reserves. If they burn all the stuff that they own that is so valued, it's just not sustainable. It cannot happen. And, you know, they talk about this divestiture, okay? That you know, we should sell off our fossil fuel stocks. But guess what? It makes good business sense because there is no way that those companies are worth what they're valued at. It can't work, okay? I don't think. So that's a little investment advice, okay? And in the Cretaceous, look at sea level. Okay, you could drive a boat all the way up the Mississippi to northern Canada. Sea level was higher significantly. And Florida was still a gleam in the eye of the Creator. It was underwater and forming like the Bahama platforms are now. And so, with this warmer world, sea level rises, and that's the real issue that we have to be immediately concerned with. And I want you to remember these numbers, okay? In this warmer world of the Cretaceous, the CO2 concentration was 1,500 parts per million. I make my students learn these numbers. 1,500 parts per million. Right now it's 400. During the pre-industrial era, in the 1700s, it was 280. And 20,000 years ago, during the height of the glacial period, it was 180. So we know that this is colder. We know that this was warmer. And we know that this was warmer. We might expect that this would be somewhere intermediate between these two. You know, it just kind of seems intuitively obvious. All right. So what are the effects of heat on the Earth? There's two ways that heat is expressed. There's sensible heat change and latent heat change. Sensible heat change is what you can feel. So that's the temperature. That's measurable. Latent heat change is a phase change. That's like water melting or steam evaporating. So we know the surface of the Earth has gotten warmer since we've been able to make these measurements. And the bad news is that these effects appear to be greatest at the high latitudes where the ice is stored. So temperature change is greatest at the poles, and that's where all our ice is. So that's a problem. Okay? And this is just a graph of the global average temperature over time. And it seems to have flattened out kind of for the last 15 years. It happens before. And some folks draw a line through this and say the temperature isn't increasing anymore. But you know what? Environmental data is very noisy. I always tell this to my classes. Environmental data is very noisy, and you need long records to see it. So the long-term record is 1.6 degrees F per 100 years. This recent record is only 0.4. But this is a 15-year record. So, you know, you really got to take the whole picture into account when you talk about this kind of stuff. And not only that, that's the temperature of the atmosphere. Okay, and the atmosphere only stores 3% of the Earth's heat. The oceans store 90% of it, and they are increasing in their heat content. Okay, so there's that 15-year record in the ocean, and the oceans are getting warmer. Okay, now this is the problem. Okay, now let's talk about phase changes. Okay, phase changes, you see melting glaciers. Here's the Mendenhall Glacier in 1937. Here it is today. You can see that it's, not only has there been a lot of development around here, okay, going back, no houses, glacier. Today, houses shortened glacier, so that ice is melting. That's a phase change. The ice sheet in Greenland is melting. That's another phase change. And since 1979, the Arctic Ocean has gotten smaller. The ice cap over the Arctic Ocean has receded, gotten smaller and smaller. And you can make a graph of that, and it's noisy. Okay? And you can see that it was really low here, and then it came back. Does that mean that things are okay? I don't think so. It just means that it's a noisy record. Environmental data is very noisy. You need a long-term data record to discern the trend. Okay? So the ice sheet's getting smaller. And the problem with that is twofold. Number one, all that polar ice, well, if it's on land, it runs into the water and it raises sea level. And the other thing is that it decreases the Earth's reflectivity. Okay, so if you've ever been snow skiing on a bright sunny day, you know you have to wear sunglasses or you'll be blinded, right? Because there's so much reflectance of sunlight off the snow. Well, the Arctic Ocean does the same thing for the whole Earth. That Arctic Ocean covered with ice in the summer reflects sunlight. A water-filled Arctic Ocean absorbs sunlight. Whoops, wrong button. A water-filled Arctic Ocean absorbs sunlight. And so that's going to change the Earth's heat balance, right? I said at the beginning, it's 50% reflectance, 50% absorption. As we decrease the ice, we change the planet reflectance, and we increase the heat. And this is another positive feedback. So as we melt the ice, we increase the heat absorption. We melt more ice, we increase the heat absorption. It's just like that CO2 thing. It's another positive feedback, but this one's based on reflectance instead of on infrared absorption. It's based on reflectance of visible light. Okay? Okay, sea level. There's global sea level and local sea level. Global sea level has to do with the level of the whole ocean. Local sea level, you have some subsidence and moving up and down of the land. Okay? And what controls global sea level, that's what we're concerned about here in Florida, is two things. One is ice volume, okay? The glacial ice volume that's stored on land. So the ice in Antarctica and the ice in Greenland. Because as that ice melts, it flows into the sea and it raises sea level. The other thing is the ocean temperature. Because when water gets hot, it expands and it takes up more room, okay? So as we melt ice, we raise sea level. As we warm the ocean, we raise sea level. So both of these things contribute to the rising sea levels that we are experiencing. And then local sea level is controlled by the emergence or subsidence in the land. In Scandinavia, where all those glaciers used to be, the glaciers melted, the land is rebounding. Okay? The land is rising. They don't have a problem. Here in Florida, we have a problem. So this is what the coast of Florida, this is what Florida looked like 18,000 years ago at the height of the last glacial period. So that's when all that ice was stored on land, and it was cold, right? So sea level was much lower 18,000 years ago. It was 300 feet lower, okay? Are we good? Okay. And then the glaciers started to melt, and this is a sea level curve. Here we're going back from 0 to 20,000 years ago, and here we have on this axis meters, okay? So here up here is sea level today, and then at the height of the glacial period, sea level was low, and then it came in as the glaciers melted. So this is like this is a sea level curve, okay, from the last glacial period. It was low, 300 feet lower, 120 meters lower. It rose really fast as the glaciers melted, and then it kind of got into this stasis. We call this a still stand. So for several thousand years, there was kind of a still stand that the sea level reached an equilibrium. And as a young person, you know, the sea level was thought as a constant datum. The sea level doesn't change. We measure all of our elevations relative to sea level. Sea level was a constant thing. Who would think sea level could change? But we've learned a lot in the 40 years since I graduated from New College. Okay? And so these are tide gauge records for Florida. And you can see that Louisiana has a serious problem. Their tide, these are in millimeters per year. Louisiana, it's 9.2 millimeters per year. All around Florida, it's 1.8, or basically 2 millimeters per year. So this translates, our sea level rise rate of 2 millimeters per year is 8 inches per century. That's the 20th century still stand, 8 inches per century. That's an increase like this. Louisiana, 36 inches per century. That's because Louisiana subsidence because of a lot of the things they've done around the levee. They've diked the levee. They've extracted oil and gas. So Louisiana's sinking big time. Florida's pretty much staying at the same place. And so that 2 millimeters per year or 8 inches per century, that's the global sea level rise rate. Okay, Florida is a stable platform. 8 inches per century is the global rate of sea level rise. Okay, this is the tidal gauge record at Cedar Key. And you can see the mean sea level rise. This is the data that these numbers are based on. Okay, 1.8, 1.9, all over the state, right? And that data looks like this. That's a noisy record. Environmental data is very noisy. And you have to have a long-term record. So this goes back to 1938. And you need a record that long to discern the trend because the noise is so great. So when somebody says, oh, it's a really cold winter, where's global warming? Show them something like this, okay? Because environmental data is going all over the place all the time. There are a lot of things that control it besides the long-term trends, okay? So it's a noisy record, and you have to observe it a long time. And there's going to be a lot of variability in the system. It's a very variable system. But there's a trend there, right? And we observe that trend at multiple stations. In Cedar Key, at Mobile, at Key West, at Key Biscayne, at Jacksonville. So that gives us a lot of confidence that that's the rate in the 20th century, the last century, okay? This is sea level rise from a culmination of many, many tidal gauge records. That's what that was a tidal gauge record. And now we can also measure it from space, from satellites. And the satellite data falls right on top of the tidal gauge records, giving us increased confidence. And what you see is the beginning of an exponential trend that looks like the CO2 curve. And so in the 20th century, going back to 1938, we had 8 inches per century, or 2 millimeters per year. And now this rate has accelerated, and right now it's around 3.2 millimeters per year, or 13 inches per century. So that's we've already can observe a 50% rise in this century compared to the last century. It's gone from 8 to 13, okay? And we might expect it to continue to accelerate as the ocean warms and those glaciers I showed you continue to melt, okay? So this is another look at this, and then that's the altimeter data. The satellite data is in red. The tidal gauge records are in blue. So we have a lot of confidence in this data, and the rate is about, right now, the instantaneous rate in the early 21st century is about 13 inches per century. 13 inches per century. Yes, sir.
Do you take into account also the heat storage in the Pacific and the influence on the El Nino and La Nina cycles?
Sure, that's part of that variability. So this is the global average all over the world. Yeah, all that stuff obscures the bejesus out of it. Makes it really hard to figure it out. Yes, sir. Uh-huh. Uh-huh. Well, we may be... Well, going back to my... Going back to this graph here, you know, the CO2, or let's just go to this one. The CO2 never got above 280 for 1 million years. And there was a correlation between CO2 and temperature. So that 100 part per million CO2 variation was accompanying an 8 degree temperature shift. And so we've added another 100 parts per million of CO2. So don't you think that it might rise? And that's all industrial. That's right. It's a correlation. And that's all I'm saying. That's what shoves the rock off the hill. And then that's exacerbated and driven. That little bit of sunlight change is not enough to drive 8 degrees C temperature change. So you need this positive feedback between CO2 and temperature. And the positive feedback. No, it's what drives that's what drives that that has driven that little change there drives the CO2 to go, the temperature to go up, and then it goes up a little bit, and then the CO2 goes up with it, and then the temperature goes up with it, and the CO2 goes up with it. And so as the CO2 goes up, so does the temperature. And let me just say this again. We've added industrial processes have added another 100 parts, and it's going to be 700 parts per million. So you can't really expect the temperature to stay the same. It would be a miracle if it did.
I'm not saying stay the same. I'm saying, yes, the extra CO2 from the Industrial Revolution has accelerated the rate of change of heat.
Yeah, it's increasing the temperature. Right. And then that will affect sea. We might go back into another. Yeah, we might go back into another glacial period. Okay. I don't think so. All right. So going back to what is predicted here, here's the rate of sea level rise. We're at, currently the rise is 13 inches per century. And we expect by the year 2100, as the CO2 concentration has gone to 700 parts per million, and the glaciers have continued to melt, that sea level rise will be somewhere, and here are a number of estimates, okay? And they range from about 17 inches to about 36 inches per year. The most conservative of these is the IPCC, the Intergovernmental Panel of Climate Change Prediction, which is 17 inches per year. All the others are significantly greater than that. And the IPCC prediction is based only on the thermal expansion of seawater. And there's two processes that control sea level. One is the expansion of the water because it warms up, and the other is the melting of the glaciers. The IPCC is a consensus organization, and all the countries of the world have to agree on what they say. And some countries, Saudi Arabia, for example, have limited what they're willing to project. And so this 17 inches is based only on half of the processes that are occurring. And so these other ones are more considering both the melting of the glaciers and the thermal expansion. So here we have loss of polar ice in the Arctic, and you can see that it's decreasing. We can measure this from satellites now. We have mass wasting of the glaciers in the Arctic, and this is in the Antarctic. So both of these ice sheets are giving up water to the oceans and melting. And so you can expect that sea level would rise more than the 17-inch conservative IPCC projection. And here are a number of these projections varying from 20 to 55, 20 to 39, up to 86 inches, okay? So most scientists, the consensus is that we can expect about a meter of sea level rise by 2100. And of course, the issue for Florida is that our coastal gradient is very low. And so when you have a 1 foot vertical rise in sea level, that translates into tens to hundreds of feet of shoreline retreat, okay? So rise it this way, it goes way back this way, okay? So shoreline retreat is much the horizontal loss of shoreline is greater than the vertical expansion of the sea. Okay? And the most vulnerable places, of course, are Miami. This is a map of impacts for sea level rise in terms of money. Miami and New York, or the green circles are money, and the red circles are human population. So Southeast Asia is very vulnerable in terms of both population and money, and mostly here we're vulnerable because of the expense of what's been built at low sea levels. Okay, so when people are asked about this, do you think human activity is a significantly contributing factor in global mean temperature? These are different groups of people. This purple one is the general public, and about 58% of people in the general public agree with this. If you ask non-publishing, non-climatologist scientists, the number goes up to 78. And as you get more active researchers and as they learn more and more about climate, the number gets even higher. So right now, 97% of climatologists who publish peer-reviewed papers on the subject of climate change think that human beings are influencing climate change. People that say no in the general public is 38%, but all these other categories are much smaller, okay? And when you poll people, this is a poll that just came out in this year. It's at Stanford University, New York Times poll. If nothing is done to reduce global warming in the future, how serious of a problem do you think it will be for the United States? And 44% of everyone thinks it's a very serious problem. 34% say somewhat serious. And so 78% of the general public think this is a serious problem. Okay? These numbers in parentheses are people in the Republican Party. So even 54, most Republicans think this is a serious issue. Okay? So for some reason, the issue is obscured, and there seems to be all this disagreement. You know, like, oh, scientists are in disagreement about this. Oh, the public is confused. The public doesn't know what to think. The public thinks it isn't happening. But in fact, when you ask the public, most of them think that this is a serious issue and that it's caused by human beings. And so the politics behind this are the same politics that were used to obscure the role of smoking and cancer, smoking and disease. You have these moneyed interests that want to perpetuate what they're doing. And for years, they put out misleading information and false research about the effects of smoking. And so it's the same thing with climate right now. There's a resistance to change that's solely based on financial interest, okay? And so I'm going to stop with this slide right here, and we can ask questions or we can debate. Maybe you and I could talk later and let some of the other people have something to say. Yes, sir. Yeah. Mm-hmm. Yes, fresh water between 4 it does, but no, salt water doesn't do that. Salt water expands as it warms over the whole temperature range from 0 to warming. That's just a freshwater thing that makes lakes overturn, so it's important, but salt water doesn't have those properties. Yes, sir.
Yeah, I'm curious, according to your graph, we should, at some point in the future, be expecting another ice age.
Mm-hmm.
Is the carbon rise enough to totally mask that, the global shifts and things? Is that enough? Has there been any research done?
Usually those interglacial periods last from 10 to 20,000 years.
Oh, so that's a big number.
It's a big range of numbers. And when accompanying that shift from interglacial to glacial is a decrease in the CO2 concentration, it's hard to see how that could happen now. You know, it goes from 280 back down to 180. We're at 400 going to 700. So I think that period of time when the climate was doing that oscillation was called the Pleistocene. I think, and a lot of other people think, that we have left the Pleistocene behind. And we're in a period that we might call the Anthropocene. And you know, the question comes off, could one species affect the whole climate of the whole Earth? The Earth is so big. Can one species change it? And the answer is yes. You know about the oxygen revolution 2 billion years ago? A species of bacteria, cyanobacteria, changed the whole Earth. They created oxygen. And the whole Earth was transformed by one species of bacteria. So if this bacteria can do it, certainly we can do it too. You can see us from space, you know? I mean, so I think that, I don't think we can count on return to glacial conditions to rectify the situation. Yes, sir.
I've read that there's a lag between the temperature and the consequences which we see. Let's say that's about a 30-year lag.
Mm-hmm.
Does that make sense to you?
Yeah, there's a lot of inertia in the system. It takes a long time, it takes a while for things to work through. It's a large mass that is going to change its temperature. So I don't know what that lag would be, but there obviously is a lag. When the last time the Earth's CO2 concentration was 400 parts per million, it was a significantly warmer Earth than today. We're talking about, processes that are basically geologic on a time scale. And we've made this alteration in 200 years, which is the blink of an eye. It's just a blink of an eye. Already we can see a response on the Earth, but I don't think that the full response has occurred yet to what we've done. So yes, I'd agree with that.
Yes, could you address the issue of freshwater aquifers and reservoirs with the saltwater intrusion as the sea levels rise?
Sure. Here in Florida, we get our water from groundwater, and that's stored in these rocks, these carbonate rocks that are under our feet. And as sea level rises, that higher sea level will invade those aquifers from below, and especially along the coast where most people live, salt water will intrude into those aquifers. Some places, you know, like in Holland, they can build dikes and keep the sea out. But that won't work for Miami because the rock and the soil underneath the state of Florida is so porous that water can move right through it. And so diking is not going to be a solution here. Yeah, go ahead. I can hear you. I think we can hear you.
Q&A etiquette. Thank you so much for your presentation. I found it fascinating and for a lay person, profound.
Understandable, I hope?
Very.
Okay.
Now, having said that, and this maybe is more of a political question than a scientific one, so if you want to say, sorry, that's not my pay grade or that's not my field of expertise. We don't have a political system that can even, pass a bill to protect us, from Homeland Security funding for more than a day or a week, or I guess now we've got a bill. And so I take that political system and I superimpose it onto your graphs, and I say, they can't pass a budget. How are we going to deal with this issue from a political standpoint in the United States, let alone you've got China now that is, I used to not worry about China because I thought, well, that's their air over there. Well, you put the pin in that balloon for me. I need to worry about China's air too. So how do we take this data and do something about it because it's a political solution, isn't it?
Yeah, well, I think there is an awareness of this problem. If you look at those numbers I put up, people in this country recognize this is a problem. Even the Republican Party recognizes it's a problem. And it's just I think things can turn around in a heartbeat, Things can change so fast. And look at the issue of gender equality and all this gender stuff as just, who'd have thought that, that would change so fast. And so we just have to hope for rapid change on this issue. And the fact that Rick Scott would even meet with us and say, 4 years ago, or when he ran the last time, he wouldn't even, this is bunk, it's not right, it's bull, And now he meets with us and he doesn't say anything because he can't. But, Florida has not joined in the lawsuit to fight the EPA regulations against coal. Other states have, but Florida has not. So I have some hope about that. And
thank you.
Yeah.
When you put a pail of water in bathtub, and it raises the water in the bathtub, the amount of floating and jetson floating around, in particular the 506 area, the one in the North Pacific, that is supposed to be about 300 miles wide, how much effect does those areas have?
Oh, the trash you're talking about? Yeah, I think that's a unique problem, and I think it's horrible, and it may affect the food web because there's so much plastic in the ocean. I don't think it's going to really affect sea level, but it's its own issue. That's a terrible thing.
Jeff, are you comfortable with the term global warming? In other words, I never say global warming, I say global weirding. And I explain to my friends that what it means is that it's either too hot, too cold, too wet, or too dry. For example, let's take California. Let's take what's happened with the weather in the Northeast, which, by the way, I just wanted to ask your opinion, is also could be part of this changing pattern. The ice melting could have an effect on this horrible cold snap that the Northeast is experiencing. So do you think there should be maybe an effort to not say global warming and say something else?
Well, I think, when you add all this extra energy into the system, because those greenhouse gases trap more heat at the surface of the Earth. So that does two things. It causes a long-term trend, like you see here, which is global warming. But it also increases the climate variability. So when you juice the system, you make the noise higher. Okay? And that's what we're seeing with all the weirding that you're talking about. Not only is the trend increasing, the rate of temperature increase, but the variability about that change is increasing as well. And that's just as disruptive as this other trend. And so, like, in the winter of 2014, all these flights were canceled. You know, there was a loss of economic activity, and the gross national product for the United States actually went down in the first quarter of 2014. And it was all caused by the weather. And so, you know, weather disruptions have the potential to disrupt economic activity and lower our standard of living. And that is the real issue. The Earth itself is going to be fine. You know, like, we'll go back to the Cretaceous. Maybe we will. But, so the Earth will be fine. It's the human civilization that is the issue. Yes, it's back in the back.
Are there any technological advances on the horizon that could help us if we continue in this state of paralysis? I'm thinking a few years back, I seemed to see a lot of articles on capturing carbon and injecting it into the earth. Now I don't see that anymore. Is there anything of hopeful value?
It's the carbon capture and sequestration. We could have built a carbon sequestration plant for every fossil fuel plant in the United States with the cost of the Iraq War, but we spend it on warfare instead. And so those things are possible. Right now, we don't want to spend any money. We can't even get the will to fix a bridge, you know? And so there's this paralysis in the government. The private sector is moving ahead with solar power and wind power. That's great.
Is there a point of no return where the methane and CO2 coming out of the earth and the ocean will compound so fast that we will never be able to go back?
I hope not. I think that a lot of people project these fears, and that, you know, the gas hydrate thing is probably not as bad as we thought. I think the carbon bomb issue in the Arctic isn't as bad as we thought. The trends of sea level rise, I don't think we're going to suffer a fast death. I mean, you know, I think it's the, you know, environmental change that we talk about, these shifting baselines, and it's a slow degradation of the environment, and I think that that's probably more likely to be the case, you know. And so even in America, we're worried that our children aren't going to live as well as we are, you know, that the standard of living will decline. And so I think that that's more of a concern. It's like smoking.
The United States and Europe could have probably addressed this issue, but how do you solve the long-term problem without the cooperation of India and China, which basically are tending to ignore this problem?
Well, didn't Obama just sign a memorandum of understanding or something with China happened recently?
Yeah,
and
but
so
they have 30 years to impact that.
Yeah.
And quite frankly, I'm told by the Florida DEP that like 50% of all the mercury air pollution arriving in Florida is coming on the jet stream from China.
That's true. Well, we just have to set a good example, I guess. Okay.
Two books have influenced me recently. One is Naomi Klein's This Changes Everything, which is incredible, and George Marshall's book called Don't Even Think About It, which is about the psychology of why people don't accept climate change. Both books argue that we will not find a technological solution to the problem. We are going to have to live a simpler lifestyle. We're going to have to be less wasteful. We're going to have to go back to really the 1960s and 70s in the way we travel and think about life, and that's why it's so difficult for us to make the change, that we will have to change our wasteful lifestyle. I'm wondering what you think about that.
Well, I would like to hope that we can remain comfortable as we are now and get to do the things that we can do now, and I wouldn't want to give anything up. I'm like the rest of us, you know. I hope that we can solve this problem. I don't know. But you might, I mean, you know, sure, it's possible.
Could you address the situation with methane? I keep hearing it's exponentially worse than CO2.
Right.
And it could be reversed if everybody became a vegetarian.
Right. Methane is the other greenhouse gas, the avis of greenhouse gases. It tries harder. And so the concentration of methane in the atmosphere is 2% that of CO2. And yet its global warming potential is 25% that of CO2. So it's a much more stronger infrared active molecule. And it also absorbs in regions of the infrared where the Earth re-radiates infrared back to space. It absorbs in those windows of re-radiation. And so it's, on a molecule for molecule basis, is 25 times as stronger. Sources of methane are easier to deal with. The number one source right now is natural gas infrastructure and recovery with all this fracking. When you mine more methane, you spill more of it, and so that is an issue. Cattle feedlots are the number 2 source, and landfills in the United States are number 3. And so
before the Industrial Revolution, what kept the carbon dioxide at 2, or what kept it in check? With the positive feedback, you'd assume it would just keep going and going.
Yeah. Well, what would happen is, again, those orbital variations would change. Okay. And so the amount of sunlight reaching the Earth would decrease a little bit. And oddly enough, it was the temperature of northern hemisphere summers that would drive the Earth back into a glacial state. So you'd have a cold summer, and all the snow in the north wouldn't melt. And that would increase the Earth reflectivity, and that would make it colder. And then, as it got colder and more ice stored on land, the oceans would drop, and you got increased dust on the Earth. So in a glacial state, you have higher dust content, and dust contains iron. And iron is a micronutrient that fertilizes the oceans. And so you'd have what they call the biological pump, okay? And the biological pump would fertilize the oceans with iron, and that would draw down CO2, and that would make it colder. And then, so you had this 2 positive feedbacks of increasing ice content on the land, increasing the reflectivity, making it colder, and then drop in sea level and in higher dusty conditions, which would enhance the biological pump and remove CO2. And those 2 things in concert would bring the Earth back into a glacial state. So what you need to lower the temperature and go back into glacial state is more ice pack and lowered sea level, both of which trends are opposite to what we're doing right now. Mm-hmm. No, that's a wild card. Yeah. Mm-hmm. Yep. That's a wild card. Yep. That could bail us out. It could. It could bail us out. It's really a difficult thing to predict and model. And so there's not any really good models that handle clouds at all. Let's take
we can take maybe 2 more questions.
Okay, over here is some, yeah.
My question is, what will if the ice caps melt? What will happen to the Earth's angle of rotation, on its axis?
I don't know that it affects that. I can't answer that. I've never heard that. I don't know. Less or more?
Given that 3% of climatologists don't agree with this, and I guess my question is, ExxonMobil probably funds a great many. Is there anybody left that isn't being funded that would have a reasonable argument?
You can always find a scientist to disagree with you. They're a disagreeable bunch. And that's why it's so remarkable that 97% of them have consensus on this issue. I mean, you get 3 scientists in the room, you're going to get 3 different opinions. I can promise you most of the time that's going to be the case. you submit a paper to review, you'll be amazed at what people come up with. So that you know, they're a very disagreeable bunch.
I'd like to thank Jeff tonight for sharing his expertise. And we'd like to thank you all for coming out once again tonight to New College to share with us.